Okay, so to start with the analysis of an algorithm, so let's first agree on what do we mean by analyzing an algorithm. What should we analyze? Actually, what we analyze in an algorithm, we mean that we need to predict, or let's say, analyzing an algorithm, analyzing the performance of the algorithm. There is something that we call complexity performance, or which means actually how many resources and what kind of resources this algorithm require. And sometimes we have the performance that, for example, if this algorithm can obtain the best results or whatever. Okay, so for us, what we will be doing, actually, we know that we have a problem. We need to find an algorithm to apply the solution, so to resolve this problem. Um, and once this algorithm is found, now what is the complexity of this algorithm, or what are the resources that we need for this algorithm? So when we say about resources, we can talk about hardware resources, but nowadays actually the hardware resources are all are present. So we have the hardware resources. So let's say, for example, I have an algorithm that I can write on my computer. I know that I will be using the CPU, I will be using the RAM, I will be using, whatever is inside the motherboard. So this actually, we consider that this is given. Now, given these resources, what is the running time of this algorithm? So, for example, sometimes an algorithm will get to the solution like 1 second. No, sometimes it will take the algorithm many hours or many days or I don't know, many weeks. Okay, to get the solution. So we most often are interested in computational time that we want them to measure, and by analyzing actually several candidate algorithm for a problem, we will select one which will be the most efficient. So for example, if you want to do sorting, there is actually several technique of doing sorting. So which one do you prefer to use? Then you will select the most efficient one, and then we can sometimes we will have a most efficient one. There is also several efficient techniques, but for some problem this is convenient, and for other problems the other method will be convenient. Okay, so it is very important actually to know which method is convenient for this problem or for the other problem. It's very important that we have these algorithms analyzed. Once they are analyzed, we can know which one is convenient for which case, and which one is efficient, and which one is not efficient. Okay, so so to analyze the efficiency of an algorithm, the algorithm is a set of instructions. And we know that in the RAM model, the random access memory that we have, the instructions are executed one after another. Okay, so one after another. Sometimes, okay, you have your program written. Say, okay, my program is 3 lines, so it seems more efficient than a program which is 200 lines. No, this is not true actually, because when we say 3 lines, we mean three instruction, and three instruction because maybe sometimes you will have 3 lines your code. In this 3 lines, we will have, for example, two simple instruction and one method that has actually behind I don't know, thousands of instructions. So when we say instruction, we mean an elementary instruction, like when we say int a, b, c, when we say a equal b plus c, when we say a for loop, while loop. This elementary that we have seen in the fundamentals of programming. But here, actually, you might ask me a question and say, but sometimes, in some languages, I have just a function that can do the job. So what should I consider this instruction or this method? I will say that we need to look for the complexity of this. So to analyze the complexity of the algorithm, we will look at the elementary instruction. This is on one hand. On the other hand, we will look at the other methods and we will say, okay, this method will have this complexity, this method will have this complexity, and then we will sum up all the complexity to get the global or the total complexity. Okay, so one should precisely define the instructions of the RAM model and their cost. What if the RAM had an instruction that sorts? Then we could sort in just one instruction. No, actually, because as I said, an instruction that sorts, this is actually a method, and this can't be considered as only one instruction. And each instruction, actually, each elementary instruction actually should take a constant amount of time. Okay, so the time taken by the insertion sort procedure depend on the input. This is actually very important to consider, because when the input size actually, for example, for the sorting algorithm is small, so I mean, uh, all algorithms will have maybe, I mean, similar performance, but we will start to realize the difference in complexity when the input size is actually very big. So we will consider both the input size and the running time. Okay, this actually you can skip. Let's say that the input size can be a length of the vector, or sometimes it can be the number of bits, depending on what we are solving. But this is more the people that work in very low level programming. In our case, we will be more in this case where the number of items actually will count. Okay, so now let's move to define the running times. So the running time of an algorithm on a particular input is the number of primitive operations or steps executed, or we can simply say the number, let's say, of elementary instructions that we apply usually, and we should pay attention that not everything that we use are elementary instruction. Okay, and we will consider that every instruction will have a constant complexity time that is independent of the length of the input. Now what we are going to do next, actually, we are going to start to analyze the complexity analysis of, or let's say we are going to analyze the complexity performance of the insertion sort algorithm.